So far, how many operations do we have on vectors? We have scalar vector multiplication and vector addition. What is scalar vector multiplication? If I have an n by 1 vector and a single scalar, what does it actually mean? N scalar multiplications, right? So a single dot, a single a times x, actually represents n multiplications underneath. We just suppress all that information. What is vector addition? N scalar additions. Claim everything that we do from this point until like lesson 20 something, or I guess lesson determinants is a little bit different. Everything that we do up through determinants and then after determinants will be based on these two operations. All of linear algebra is multiplication and addition. Does that make sense from the standpoint of a linear function? Yep. What is linear functions? Y equals mx plus b. You have scalar multiplication and scalar addition. These are the fundamental operations in all of linear algebra. Pretty cool, right? Doesn't seem so bad, right? All right, so here we go. We're going to say that these are the algebraic properties of vector arithmetic. Okay, so we'll have, can you guess the things that we need in order to discuss algebraic properties? We need vectors. And then also suppose we probably need some scalars so that we can talk about that. Then, all the following hold. We'll do one or two proofs. So we're going to talk about commutativity of addition. And I suppose we could say vector addition, right? Could you guess what commutativity means? Yeah, that's a very, very intuitive verbal description. X plus y would be equal to y plus x. Why would that make sense? Underneath this, what's happening? N scalar additions. Every single scalar addition is commutative, so you can literally just put it on the inside, turn it, and then put it on the outside, right? And we'll see that in a second. Could you guess the other ones? Yeah, so we're going to have something called associativity of vector addition. Could you guess what associativity means? I could first group y and z, then I could add x, or I could group x and y and add z, or I could care less about what order I do it in. Right? Doesn't matter how I associate it. At the end of the day, I'm going to get the same thing out. All right. Let's talk about something called the additive identity. Indeed, confirming this is a group. So if we say that x plus 0, could you guess what 0 is? Yeah, so this would be an n by 1. This would be an n by 1. What is the 0 vector?
0.
How many rows? How many columns? 1. Could you guess what this is equal to? X, and it would also be equal to 0 plus x. So additive, it's the mathematician's favorite trick. I can add 0 and it doesn't do anything, right? If I didn't specify the dimensions of this thing, what would they be?
The same as the x vector?
Yeah, I almost wanted to ask Chandler for that one. If I didn't specify specifically what the dimensions for 0 would be, how would you know what they would be? They must be the same as x in order for this thing to be defined, right? Okay, so let's talk about something called an additive inverse. Could you guess what we say about additive inverses? 0. And that should probably be equal to negative x plus x, and that will always happen. So if I multiply x by negative 1, this is a proof. Negative 1 times x is the additive inverse of x. Oh, yeah. All right, so now we have what we call distributivity of scalar mult over vector add. Could you guess what that means? So if I scalar multiply over vector addition, could you guess what that one is? It would be a times x plus a times y, where both of these multiplications are now what type of multiplications? Scalar multiplications. I'm going to encourage us to train ourselves every time we see a little dot for our multiplications. First of all, I like to write them. And then second of all, I want to know what type of multiplication do we have. I can think of at least 3 types of multiplications and at least 9 different ways to interpret those in this class. And I want to train us to get used to thinking, wait, what am I doing here? What sizes are the left and right arguments of that multiplications, and what does that immediately imply about the operation? So now we're going to talk about something called distributivity of scalar add over scalar vector mult. Could you guess what that means? If I take a plus b and I scalar vector mult with x, could you guess what that one is? A times x plus b times x. So I can first add in a scalar space and then multiply by a vector, or I can do both of these. In a computer, we would probably prefer to do this because that's one addition plus n more multiplications. In this is n multiplications, n multiplications, n more additions, right? So that's beyond the scope of this class, but it's a kind of a useful thing to think about. How would you code up a thing, a data structure and corresponding operations to be as fast as possible. The other thing we're going to talk about is called associativity of scalar multiplication. So could you imagine if I had a times b times x, and the first thing that I did was to do b times x? What another way we could write that? A times b times x, and another way we could write that is a times b times x. Yep. Where is the addition operator? You're asking me what the difference between number 5 and number 6 is, and I would ask you, what is this addition right there? Vector addition. What is that addition right there? Scalar. So what's the difference?
Vector addition versus scalar.
One of the distributivity has to do with adding vectors and then scalar multiplied. The other one has to do with adding scalars and then scalar vector multiplied. Yep. And then the last one is called the multiplicative identity. Could you guess what 1 times the vector x is? Is this 1 a vector or a scalar? Must be a scalar because this multiplication, the only one we've talked about so far, is scalar vector multiplication. Could you guess what 1 times x is? X. When you multiply by 1, you don't rotate and you don't change lengths. It's the only scalar in all scalars that you could choose that doesn't do anything to the vector. It's the identity, right? Would you like to prove one of those?
Yeah.
Which one would you like to prove? The moment we prove it, what do you think the likeliness that it will be on your exam?
The value of a problem is not.
Sam, you're good, man. You gonna be a lawyer?
No.
No. Yeah. I might actually go for one that has more than just one multiplication in it. I would probably, if I were you, I would request one that has multiple operations in it.
5 or 6.
5 or 6? Maybe let's do 5. Okay. So let's prove number 5. Okay. So what do we need to prove number 5? We need a scalar, and what else do we need? 2 vectors in Rn. So then let's consider a times x plus y. Okay, well this is going to be a times, and then I'm going to need a big one here. What's x plus y? Well, it would be x1, x2, all the way down to xn. And then I would need y1, y2, all the way down to yn. Okay, well, what does it mean to add those two vectors together? What does vector addition mean? Scalar addition in the n components, right? So this would be y1 plus x1, x2 plus y2, all the way down to xn plus yn. What does scalar vector multiplication mean now? Yeah, so now I've got this thing a times x1 plus y1, a times x2 plus y2, all the way down to a times xn plus yn. This multiplication now exists in the space of scalars. What does that immediately mean if that multiplication exists in the space of scalars? What can you do with it? Distribute. That's called distributivity of scalar multiplication over scalar addition. So what would that be now? ax1 plus ay1, ax2 plus ay2, all the way down to axn plus ayn. Well, now you have vector here, vector there. There's an addition in between. All of these, what's the definition of vector addition? Yeah, and scalar multiplication. But math definitions are bidirectional. They're two-way streets, right? So I can start at the separate vectors and go to an individual one, or I can start an individual one and go out to separate ones. So now I've got something that looks like ax1, ax2, all the way down to axn. And now I'm going to add this to ay1, ay2, all the way down to ayn. Okay, any suggestions on that one? Yeah, well, what do you know about the first vector right there? A is in every coefficient. It's in every single entry of that thing. So now I'm going to go up here. Okay, so what does that immediately mean that I can do with A? Pull it out. How did I know I can pull that out? Definition of scalar multiplication. And what's that now? That's a times x plus a times y. What was the claim of this property? That I can actually pass out scalar multiplication over vector addition. Where did the fundamental property come from? Yeah. I assumed n copies of scalar operations, both addition and multiplication, and all of those copies had the same property that I was desiring underneath, and I could do it in any order, right? Yep.
So we don't have to prove scalar multiplication.
That is an assumption on R. Yeah, you're asking me, how do I know this stuff? You would take a real analysis class. Those are what we call algebraic axioms of the real numbers. There are 10 algebraic axioms, I think 2 or 3 order axioms, and 1 least upper bound axiom if you decide to do it axiomatically, not constructively. That comes from a real analysis class, and you can assume that those things are true here because this is not a real analysis class. Yeah. And even if you were in a real analysis class, you would still assume them to be true because we start from somewhere. That's Hilbert's famous Einstein problem, right? Gödel and Hilbert.